Xin chào. Good morning, everyone, and welcome back to HCL Vietnam TikTok series. It's such a beautiful Saturday, right? I would like to send my greetings and thanks for your represent today in virtual tech session, very large-scale integration VLSI opportunity at HCL. My name is my senior marketing, and I'm your host. But it looks like everyone is still sleeping, right? So we are waiting for more people to join.
In July 2020, HCL began its journey in Vietnam. It was also the same period when the dreadful pandemic pushed the whole world behind closed doors. But technology came to the rescue and the world remained connected. Thus, in order to ensure regular dialogue, free flow of knowledge, thoughts and ideas, HCL Vietnam Tech Talk series was envisaged. In this HCL Tech Talk series, HCL experts share ideas on technology, future of workplace, connected living, and connected enterprise. The series went live on December 2020, and since then, sessions on various high-tech technologies such as machine learning, artificial intelligence, Internet of Things, digital manufacturing, cybersecurity, etc. have been conducted. HCL Vietnam is committed to shape the technology of the next decade today. HCL Tech Talks will keep bringing many such valuable tech talks to your home screen. Stay tuned.
So for who people who have just joined us, let me share something about HCL Vietnam. HCL Vietnam started over a year ago and as on date, and we are located in two locations, Hanoi and Ho Chi Minh City. We are serving 30 plus global customers from the both locations and a diversity ratio of 27%. HCL has also successfully set up a university partnership program where we have got over 15 universities. Our focus area for Vietnam is high-tech area, which also includes digital transformations as a key focus area for us. And the domain where HCL Vietnam is focusing on from banking, insurance, other financial services, automobile, or manufacturing, pharmaceutical, medical device, CPG, and retail. We recruit people who are experienced professionals in Vietnam, and we also look at fresh university graduates and also students who are all undergoing their university education in the 7th and 8th semester. Yes, so in the next 3 years, HCL Vietnam is poised to grow to train 3,000 employees to provide service to clients in various high-tech and cutting-edge technologies. If you had interest in career opportunity at HCL, please visit our website, hclvietnam.com, and follow our fan page to find out available jobs. So attend our visual session today. We have Mr. O.P.Srivastava, Technology Director ERH of HCL Technology. So let me share something about him. Let me introduce more about today's presenters. O.P.Srivastava is currently working in the capacity of Technology Director at HCL Vietnam. He has over 30 years of experience as a VLSI professional. He has a master's degree in computer science from a leading technological institute at India, IIT Bombay. He moved to HCL Technology in the year 1996 and was one of the early starters of VLSI practice at HCL Technologies. Since he has successfully led large project teams for VLSI development for HCL international customer and had also successfully managed VLSI delivery unit at HCL for several years. So his current character at HCL Vietnam to build and manage VLSI team at Vietnam to deliver a VLSI project for HCL international clients from Vietnam. And during the session, if you had any questions, please comment below. We will answer at the Q&A session. For those of you just joining us, welcome. To begin, I would like to invite Mr. O.P. to give us the vision of VLSI. Hi, O.P.
Hi, good morning, Mai. Thanks for having me in this session today. And good morning and xin chào everyone at Vietnam. I am sure you guys are having a wonderful Friday morning. And so I will not take a lot of time here, but I'll just give you a brief snapshot of what we are trying to do here at HCL Vietnam, and also about what I particularly have been doing for the last 30 plus years in the VLSI industry. So to start with, we will talk about many of you who are probably new to this word VLSI, very large scale integration. What exactly we mean by it, and what it has in store for us. So Mike, could we change the slide to the next one? So this is a slide that gives you a very high level view of what VLSI is about. So those who are from electronics background, they would probably understand and agree with me that electronic circuits are basically realized by using millions and millions of transistors, bipolar junction transistors or field effect transistors in various configurations to generate, various logical elements, sequential or non-sequential, and that is put together to realize, electronic circuit for end and target application. So VLSI is the process or the field which actually goes about integrating these, various, field effect transistors into a very, very small die, so that the design can be, compressed and miniaturized in to a size that can be, easily handled and managed by people, and thereby enable the, adaptability of these technologies in the everyone's life. So, for example, the first computer that you must have heard of, ENIAC, which was produced for the first time in 1944, was using, electronic valves, and it actually occupied a full 15 cross 10 square feet of, room. So there were lots of big panels, and the circuit was very huge, and it was doing a very limited function, and also it was very, very power consuming and not very fast actually. But it was a big step because we actually moved towards being able to, compute things automatically and at our will. So today, if you notice, I'm sure all of you are used to laptops, and you are having mobile phones which you carry in your pocket, and you'll be surprised to realize that the compute power that these laptops and these cell phones today capture is way beyond what was actually, realized in that, a huge machine that was, invented the first time. So all this miniaturization happened because of VLSI. Because of VLSI, today you're able to, have a very, very convenient and smooth day-to-day life. You're able to communicate. You're able to, in every walks of your life, you're able to use electronics and benefit from the advantages, and that has been all enabled by VLSI. So, so if so that answers my the second question. why VLSI? So first of all, it brings in miniaturization. It makes the circuits really small to be leading to the ease of handling, and because the logical elements have been reduced greatly in size, it also leads to lower power consumption because the excitation voltage is required for the switching circuits also reduces because of size reduction, and for the same reason, this also leads to higher speed of operations. So today you are doing millions and millions of transactions in less than a second, that was not the case when the computers were initially invented, let me say. So the entire this journey from what we had started and where we are today is because of VLSI. And as far as the application is concerned, I'm sure you will agree with me that it has touched every aspect of our life. So if you are using a cell phone, or you are commuting, or you are taking some medical services, everywhere you'll find that electronics has come in a big way. Today the medical science has benefited greatly by VLSI. Lots of high precision life saving equipments are available for public usage at an affordable price because of VLSI. Your aerospace, your defense, your automotive industries, everyone is benefiting from VLSI and the convenience that it has brought to the electronics world. So it definitely is at the core, at the bottom of everything that we have, today in the name of automation, in terms of in terms of technology. So VLSI is at the base of, at the bottom of every thing that we have around us, and which has make our life so beautiful. So next slide, please. So here is something on the industry outlook. So because of all the benefits that we talked about, VLSI is having a great potential. And this slide talks about, it's basically it's a report from Forbes magazine, and it basically talks about a continuous compounded annual growth of 8.6% year on year for the next 8 years. So as you see, the industry is expected to to embrace and adapt VLSI even more than what it is doing today, and it is expected that it will more than double in the next 8 years, which means that there is a huge potential and opportunity to practice and align with this field, because it's going to offer lots of opportunities. Uh, uh, the newer technology areas, like you must have heard of artificial intelligence, Internet of Things, and machine learning languages, are going to further fuel the growth in VLSI industry. And so what this slide you're looking at is basically a very conservative outlook. Actual numbers may be even more than what you see here. So this information should give you a good reason for adopting this technology, and practice it for and pursue a fruitful and successful career in VLSI. Next slide, please. So we will talk about what it takes, how exactly this, what are the nitty-gritties of VLSI. So if you want to practice as a, start and pursue your career as a VLSI professional, then what exactly you need to do and what you'll be doing. So this slide talks about three major categories of VLSI professionals. So you could either you could decide to pursue your career as a front-end design engineer, wherein you will be dealing with the actual system requirements of the target applications, and you will go about doing a high-level architectural design. You'll also do evaluations on how much of your logic has to be done actually at hardware level, and how much can be offloaded to software if that is an option. You'll also do functional level design definition in using high-level languages like Verilog or VHDL, which is pretty much like, if you in terms of programming acumen, it is pretty much like any other high-level language that you know of, like C or C++. So you could after having done that, you would go about doing a verification of your design, because you want to make sure that whatever you have conceptualized and whatever you have put into the whatever idea you have put in is actually working to the required uh, perfection. And then you would go about converting this design into a actual physical gate level definitions, which will be taken for a physical implementation by the next set of engineers, like back-end engineers. Back-end is basically the process that is actually about realizing that your design concept, which you defined in a high level language like Verilog or VHDL or system Verilog, and then basically actually translating that into in terms of physical entity and capturing it on a substrate and on a die. So backend design is again a very, very important part of VLSI design life cycle. The engineers here are concerned with macroelectronics level details of your end target design, and they actually deal with issues like timing closure at a module level, at a chip level. They also talk about deal with the various those who are from the PCB design background, they would know that there are a lot of crosstalks or parasitics that had to be dealt with when you're doing a high speed design. So they basically deal with all those nitty-gritties and make sure that your design is actually fabricatable, and that it can be fabricated in any of the uh, foundries that we have available today. So so fabrication and validation is a third set of practitioners who basically actually deal with the foundries, get your design fabricated, and after that they carry out various validations to make sure that you actually have realized what you wanted to. So as a VLSI professional, you have multiple opportunities to pursue. So you can decide to be a front-end engineer, you can take a decision to be a back-end engineer, or you can be a validation expert, fabrication expert. It is not a common practice that a single engineer will be responsible for front end, back end, as well as fabrication in the industry, because of the complexities and the vastness of each of these field. We have very, very dedicated engineers who practice front end part of the design. There are people who practice the back end part of the design, of physical design, and then there are people who basically excel in the fabrication, foundry related issues and the post silicon validations. So next slide, please. So here it is. Here is a little deeper dive into each of these domain, and I will try to demystify many of the things that you must have heard about in these things, and basically may give you a clear perspective of what you would be expected to do in each of these streams. So front end design, as I mentioned, it starts with the specification. So you would, as you know, you'll be targeting your design for any given target application. Gone are the days when you should do a general purpose machine. For example, your laptop is a general purpose machine, so it is not targeted for any given application. It's a general hardware platform, software platform on which you can deploy any of your problem and expect to get a result. But in real life, when you are basically going for a targeted applications like automobile or your medical electronics or telecommunications, you need not do general purpose treatment everywhere. You will like to get specific and do just the needful for those respective domains. So so basically that's why there is a concept of system on chip. So basically, which for any targeted application, you will be basically realizing a system on chip, which will be having which can have a local processor and all the required electronics that going to support that particular domain. So you will start with the specification for your end application. You will do you'll define an architecture, do vetting of that, whether it basically meeting the performance demands that you may have, and you'll follow a practice called ESL, electronic system level modeling here, uh, which will be actually a very you'll actually realize and model all your design elements and connect them as your intended architectural scheme, and check for the performance, whether you are getting the required number of cycles that you want to use for a given transaction at a system level, or at a transaction level, and so on. So outcome of this specification phase is a clear definition of how much of your end target application you're going to realize by hardware, and how much you're going to realize by software. Having done that, you go about design, which is actually dealing with the various lower level details of your intended application. Nowadays, it's a common practice to use third party proven IPs, which are readily available in the market, for realizing your overall design. I mean, when you already have some reusability options available, then you need not do it from on your own from scratch, because that is not very efficient way of doing things. So you'll also be doing vetting of what IPs, what functionalities you'll develop from scratch at your end, and what you will be basically utilizing from third-party options or IPs available. Having done that, you will go about using a high level language like Verilog or VHDL or System Verilog for capturing your design intent. So the entire your bus architecture, your communication interfaces, you will basically realizing using a high level language, which is not exactly like C, but it's very much similar in the look and feel. And so this and it is commonly known as HDL, hardware descriptor languages. So back in early 80s, people used to do in a very painstaking manner. Uh, they should deal at a transistor level, and you should realize huge circuits manually, and that was a very painful process. So you would have seen that the number of designs that happened around 80s was not very huge, because the process involved was very cumbersome. But now in mid 80s, the concept of HDLs came in, and in around 90s, it has been perfected to a level where lots and lots of people are able to do design much more conveniently using these HDLs, and and have added to the momentum that we see today. So you will do the coding of your design, and while doing the coding, you will also take care of depending on how mature your organization is in terms of processes, or in terms of practice, you will have uh, predefined guidelines for ensuring that there is a very a good quality of design code that is generated, uh, which enables reusability, maintainability, testability, and also synthesis of the design. Having done your design, you will also need have a very serious requirement to make sure that the design that you have captured is actually meeting your intended objectives. So you will do so verification is the next step that you carry out, and here you are dealing with uh, verifying your design requirements. So uh, so here basically this is a very crucial part of your design cycle, because if you are not able to, if any defect or bugs seep through, then it is going to lead to a huge time and material wastages. So this is a very detailed field, and there are people who are just leading their entire career on verification alone. So here basically things like directed testing, which is basically focus testing for each of the feature that is carried out. Random testing, you also want to make sure that for a random sequence of macro operations and random inputs of data for those operations, you still remain on the track, and you don't do a faulty uh, you know operation. So this is a very uh, interesting and detailed based activity. So there are a lot of over the year industry has sensed how crucial this field is, and there are lots of standard methodologies that have been evolved to make sure that you do a foolproof job in a first go. So you must have heard of various verification methodologies like based on system verilog, uh, U, UVM, OVM, SVM, and so on. So those are the activities that are carried out here. And other thing that has been realized that with the design size increasing, uh, it has become also a very increasing requirement to complete this cycle at near hardware speed. So emulation based approaches have also seeped in over the last 6 to 7 years. So today there are EDA and non-EDA vendors who are providing emulation options, which you can use for doing verification of a design at near hardware speed. After having done a detailed verification, now is your time to actually take it to a physical implementation of the design. So the next step that is carried out uh, is synthesis. So you have to also, as you know, there are few foundries which you'll have to align with in order to fabricate your design. So like TSMC, UMC, Global Foundry, SMIC, and so on. So you basically will target your design from any one of these foundries, which means you'll be taking the library files for these targeted lab foundries and basically use that for synthesizing your design. So this is an interesting step. So as I mentioned that the most fundamental element of your electronics is transistors, BJTs, FETs, and so on. So these foundries have various library files defined, wherein using these basic elements, various logical primitives like and, or, not, your flip flops are basically realized. So when you use these libraries, your you will be presented with a output file which is called netlist, which will be having the library elements for a targeted foundry. So if you when you use that, so you will be more easily adaptable for those foundries. So this is the step which actually converts your behavioral definition into the physical definition of logical elements, which will go onto your chip or your IC. This is also the step wherein you bring in a few testability measures like design for testing features, scan insertion, built-in self-test, memory built-in self-test, and so on. And this is also the step where you carry out, depending on the size of your design and the complexity involved, you may also want to do a virtual prototyping. So virtual prototyping is basically you may take either whole design if the design is not very big, or a various part of it, and actually realize them on a hardware platform like which are like FPGA based or so on. So just to make sure that your design does work at a hardware level as well. So and this is also the time wherein you do preliminary timing closure. So basically timing closure, as you know, till now that is up to the stage of verification, you were dealing with behavioral definitions. You didn't have actual physical characteristics of your end circuit brought into your design files. Only the synthesis is the step which actually has converted your design into physical definition, and hence has also brought in the various timing characteristics. As you know, nothing happens in zero time, so there will be some timing characteristic attached to each of those and or not or flip flops functions that you would be realizing for a given foundry. So this is a test step where you actually deal with those timing definitions for the first time, and you focus on whether those are leading to any time violations which might lead to malfunctioning of your circuit. So so this is also a very detailed and detail focused activity, and there are engineers who focus primarily on STA or static timing closures alone. So after having done this five major steps, you you end up with a something known as netlist, which is actual physical entities based design definition, which is now ready for physical implementation. We can move to next slide, Mai. So what follows next is the backend design flow or the physical design flow that you are aware of. So this is basically a step that is analogous to or very close to a PCB design step that you must have come across in your if you are have been practicing, or if you have seen any hardware board, then you know that you first do your circuit design using your uh, pen and paper or some computer based methodology, and then you actually go about realizing that design onto a actual physical substrate. So a PCB uh, base on which you basically realize your design, and you deal with actual physical chips, and you connect them using copper tracks to meet your end objective. Similar thing is required here also. So here also you have a bundle of millions and millions of FETs, MOSFETs presented to you. Now you basically go about actually laying it on a physical uh, you know uh, die. So you start here, since we are dealing with millions and millions of gates, so it is a very cumbersome process. So breaking a bigger problem into smaller problems and solving them bit by bit is the approach that is taken here. So you start with a block level placement. So major functional blocks, you will place it on the die. So you will decide where your memories will be residing, where your external communication interfaces will be residing, where your cache will be residing, and where your DMA logic will be residing. So you'll mark them on a physical die, and then do a block level routing of those elements at each of the blocks. So you will do a block level placement and routing. You also do a clock tree insertion. The clock is a very sensitive thing, as you know. If your clock takes a very roundabout path, then it might lead to clock skews. The delays the clock reaching at block number one, block number A may be different from in terms of timing the block number 10 in the same design, and that might lead to a malfunction of your design. So it's a very important part. You want to make sure that there is minimal clock skews at a block level. Uh, and then also parasitics, as since you are having a, a, a physical substrate on which you are basically placing these logical elements and connecting them by wires. So there is also a likelihood of various a capacitive load developing uh, across these copper wires, and also with respect to the substrate. So you which again, as you know, can lead to malfunctioning of the signals that are involved, and you may end up with timing violations. So you want to deal with these parasitics as well. it is pretty much same as you do in your PCB design activity. I'm sure many of the people who are on this call may be also practicing hardware design of PCBs. So they can very well relate to this, what I'm talking about here. So what you do at block level, so you will do each of the blocks separately, and then you will connect them as per the system level architecture, and then do the same thing at a chip level, or the top level. So uh, and what also needs to be realized here is that here at each of the block level and at the top level, you also need to do timing closures. So as we discussed in the previous slide, that there was physical entities of logical elements realized, and there were timing characteristics that were captured, and against that you did a timing analysis and closures. But at that time there was no uh, track delay or connectivity delay that were captured, because it was still at a in a bundle fashion, and it was not really routed onto physical substrate. But now here you're actually doing a routing of those logical elements. So you'll also come across some propagation delays, depending, and coupled with the parasitics that we talked about, there are some timing delays going to be added here. So you need to do a timing closer at a block level as well as at a top level. So after having done the placement and routing, connecting them as per the design intent, and doing timing closer, you still need to do some uh, some physical design verification on your end product. So as you know, the foundries have different design rule checks depending upon their limitations. So there may be some limitations with respect to how much of spacing is required between two copper tracks, and how much of spacing is required between two metal layers, and so you need to also do physical verification of your design and make sure that it complies with the foundry guidelines. So this is basically DRC, ERC, electrical rule check, design rule check you carry out, and also LVS, which is the layout versus schematic checks you carry out. So after having done all these things, you end up with an output which is now ready for being taken to the foundry and be fabricated. It's called GDS2. It's a very, very commonly industry standard terminology. So the foundries will receive and act on only the GDS2 file that will be capturing your design intent. So once you're done with your physical design and you are ready with your GDS2 file, you move to next step, that is fabrication. So Mike, can we go to next step, next slide? So this slide is talks about what follows next. So here a big part of your activity is basically your interaction with the foundry houses. So I'm sure many of you must have heard of that various big semiconductor players like Intel, TI, Samsung, they all have their own foundries, and so when you do a design for any of these organizations, you target for their foundries. But a majority of designs today are being handled by general, uh, foundry houses like TSMC, UMC, Global Foundries, and SMIC, and so on, which are available for non fab or fabless companies. So you might so in the earlier two steps, you may have actually targeted your design for uh, any one of these foundries. So you go about sharing your GDS2 definition, which is foundry ready, and that will be presenting to your foundry houses, and what you will end up with is a wafer. So this circular thing that you see in this slide is basically is what you will end up with. This is a wafer which will be capturing multiple instances of your design at very, very lower geometries. Uh, geometries like 3 nanometer is the most recent technology node. So 3 nanometer means basically your each of your logical elements like your FETs are basically at that lower resolution, so near Armstrong resolution. So and millions of those will be captured into your single wafer, and you will be basically having something known as wafer, which you see in this picture here, available to you for doing the next step of process. So first thing you do is basically do something known as wafer sorting. So there may be some manufacturing defects in each of those wafers. So you want to make sure that your wafers are not having those manufacturing defects. So you will do something known as wafer sorting. So there are testers. There are companies which basically produce wafer tester machines. So you will be basically using them and basically weeding out the faulty wafers and saving the faultless and foolproof and correctly manufactured wafers for next step. The next step is basically now you have a wafer, but what you actually have dealt with ICs in the name of ICs or SOCs is what you see in the second picture here, which where is a there is a physical chip here with pinouts for connecting to the rest of the electronics on your board. So this is realized by using these wafers on a plastic or silicon substrate and routing from there to the pinouts on the chip boundary. So this process is called packaging and assembly. So this is the next step that you'll carry out. And after having done this phase, you will be having this actual chip that you wanted to fabricate in your hand, which you can go about doing post-silicon validation. So or you can do your target board uh, or hardware design uh, as a next step. So this is a detailed account of what you do in a VLSI life cycle. So as you see, there are various career options available. So you can be a front end engineer, and in front end engineer you can decide, you can take a decision to focus only on the system level architecture definition, or uh, design engineer, or a verification engineer. You can also choose to be a time enclosure engineer or a DFT engineer. And coming to physical design, you can decide to be a layout engineer. You can decide to be again a physical verification engineer. And coming to last leg, you can decide to be post wafer steps, that is routing, placement and routing of at a wafer level. Or you can decide to be a post-silicon validation engineer. So there are multiple career options available, and all of them are crucial and integral part of your design life cycle. So so this is one field that basically are offering you multiple career options. So we can move to next slide, please. So now, having described what the VLSI lifecycle is, let us talk about what we have for you at HCL in this domain. So to get there, let me just walk you through this slide on where we come from. So basically, we are from Engineering and R&D Services Group at HCL, uh, very fondly and popularly known as ERS. So this is a group that is basically more than 40 years old. In fact, it is a group that was the first group that was ever realized in at HCL, and most of the senior leadership at HCL is from this group only. So this is a 40 plus years old group, and accounts for more than close to 40,000 people. We call them ideapreneurship, but actually what we mean is that they are people who are basically engineers practicing this ERS service line. We have we service more than 65 of the top 100 R&D companies across the globe. And you may be pleased to know that we are second largest ERS service provider across the globe. So with a revenue of about $2.2 billion per annum, we are number one in India and the number two in the globe. So there are not many people doing more of ERS business compared to us. So on the left hand side, you see horizontals. So basically, this business unit has 6 major horizontals, which are basically embedded software engineering, hardware and VLSI engineering, mechanical prototype testing, PLM, and software product and platform. So we are from the hardware and VLSI design practice, and what we do is basically capture on the right hand side, which is under the heading verticals. So we are basically doing hardware design, that is actual hardware PCBs and systems, as well as VLSI chips for these industry verticals. For example, aerospace, automobiles, industrial, medical, office automation, telecommunication, consumer electronics, ISVs, and semi industry itself. So this is a huge service line. So we are basically having coming to VLSI, we have processes and practices perfected for and aligned with all these industry verticals that I talk about here. And since we are just now, I made a statement that we are the number two in the across the globe. So the question might arise: what enables us to be there? So for that, basically, if you see here at the bottom of the slide, there is a mention of center of excellences. So HCL does a huge amount of investment to produce value adds like IPRs or solution accelerators, which help us to stay ahead of our competition, and that has basically so R&D is a very strong culture at HCL. So we have a lot of investment going on continuously into what we are doing in order to get aligned with the emerging trends in the industry, as well as to remain ahead of the competition. Next slide, please. Thank you. So this slide is a little dive into the silicon practice itself. So silicon practice was started at HCL in early 90s, 95 to be precise. And today we account for including all the three domains that we talked about, front end, back end, and fabrication and validation. We have close to about 5,000 plus engineers working in this domain, and this base is distributed across the globe. While majority of us work out of India, that is about 80% population, but the remaining 20% is spread into various other geographies across the globe, Vietnam being one of them. So if you look at on the right hand side of the slide, there is a skill-wise split. So what you see here, that we cover all the phases of VLSI design life cycle that we discussed in earlier slides. So we have teams for RTL design, FPGA design, verification, physical design, emulation, analog and mystical design, DFT, and design automation. So at HCL, you will get a chance to practice any of these domain. So you can decide to be, if you want to do a physical design, you can very well get opportunities within organization itself. If you want to practice DFT, or if you want to practice RTL front end design and verification, so all are available and practiced at HCL under the same roof. Other thing that you might want to take note of here is that the process node. So since we have been in the industry for a substantially longer time, 25 plus is a long time, So we have worked at various, in fact, we have moved with the industry in terms of how it has evolved. So while many of our designs are like 62% designs are in the greater geometries, that is more than 16 nanometer space, but a huge chunk have been realized in the less than 16 nanometer technology, and the latest one being 3 nanometer technology for one of our customer in US. So roughly about 38% designs are in the lowest geometries that you must be aware of, and about 60% are in the old generation or the higher geometries uh, space. Our VLSI teams are spread in over 50 other countries across the globe. So there is a huge possibility of working, either to remain resident at one single location or move around and see more of technology and the world. So that option also exists with HCL. So next slide, please. So this is again a statement on what we do. So if you see here, all the we are addressing all the phases of your VLSI design life cycle, that is front end as well as back end, and also some bits of post fabrication at HCL. So except for fabrication and packaging and assembly, rest everything is done within HCL. So which is pretty much the norm with the fabless companies. So and for addressing packaging, fabrication, we have got a good ecosystem partners which are captured on the right hand side of the slide, which help us do accomplish those aspect as well. So we remain a single point contact for customer and address complete end to end or turnkey solution for their ASIC requirements. To do this, to stay ahead of the competition and be where we are today, that is second in the world, we have a very strong ecosystem also available. So if you look at the right hand side of the slide, you'll find that we are having a good ecosystem for EDA tools and IPs. So all the major EDA players like Synopsys, Cadence, Mentors are we have got alliances with them, and we also have partnerships with them for using their IPs, as well as uh, there are a few other IP providers that you see here, like Sci-Fi, Echo, Smart DB, ARM, and so on. So we have alliances to do this design on these IPs and technologies. We also have strong alliances with various foundries that you know of: TSMC, UMC, Samsung, uh, Global Foundries, Tower, and you name it. We also have prototype manufacturers uh, alliances. So if we for many of our requirements, we do prototype manufacturing and prove our design, and then the fabrication part is handled by the customer themselves. Or if they have a need, we can handle that as well. So we have prototype manufacturers alliances like IMEC, Presto, Open5, and so on. And we also have partnerships and alliances with OSAT, which stands for outsource assembly and testing. So that is the part of the fabrication, post fabrication life cycle. So this is what basically, so these alliances and ecosystem uh, strength helps us to stay ahead of our competition, and and uh, and end up with what we have realized over the years. So we can move to next slide now. So I mentioned that we also have a strong practice of investment in our people to to produce value adds, uh, which helps us to stay ahead of the competition. So this slide talks about various IPs that we have developed and we leverage for our customer projects. So you'll find that there are lots of uh, a lot of IPs that go into a typical SoC realization. So, so the processor cores, the high-speed interfaces, interconnects, security-related IPs, and various peripherals like CAN, I2C, and all those things, and memory interfaces. So, if our customer has a need to do a design that uses any of these IPs, then they don't have to go for any third party or solution provider. We ourselves leverage these IPs and help them get into a time to market advantage vis-a-vis their competition. So this is a big differentiator which helps us stay ahead of our competition, which is not common in the industry. Next slide, please. We also have invested in various methodologies and processes I mentioned. So this is one example of that. So this is a very fast framework. I mentioned that verification is a very critical activity, uh, and as it deals with correctness of a design. So we have our homegrown framework for verification, which is basically a collection of various, code snippets and reusable elements that go into a typical test bench dev- setup. So using this framework, we have established in multiple engagements that we have achieved 20% reduction in overall, uh, verification cycle. So this is again a differentiator, and basically, and it is something that basically helps us stay ahead of our, our competition. And this is again another value add. Next slide, please. I also talked about emulation, which is a hardware based verification approach, which has come into the industry in the last 4 to 5 years. So we have a strong practice around this also. So you will be pleased to know that we are the probably the only service based organization which has its own emulation lab. We are the first adopter of we are one of the first adopter of emulation based approaches and practice, and we have our own we have invested in emulation boxes from uh, Synopsys, and we also have tie-ups with other emulation options like Cadence, Mentor, to utilize their emulation solution. So this is a strong practice that we have here, and which is again a differentiator. Next slide, please. We also our uniqueness is also marked by our investment in setting up various labs. So we talked about post silicon validation. So that is basically all about it is a clear differentiation from any small time player who may not have the metal to invest in this kind of lab infrastructure. So we have more than 50 million labs billion dollars have been invested in setting up a share of the art labs in our India and global locations, which are basic as you see, which are critical for post silicon validation. So when you are done with your fabrication, you need to do one is the functional validation of a design, and second is the characterization of your signals. So whatever you signals you are going to emit out of your chip, they should be meeting certain electrical characteristics. So those validation labs is something that we don't have to go outside. We have labs within our organization, and which is again a big differentiation with respect to our competition. Besides this, we also have uh, qualification labs. So in many cases for various industrial domains like aerospace, automobiles, there are environmental qualifications required for the end chip. So we have in-house qualification labs, and we don't have to go and to any outside agency. So that again is a big differentiator and helps us in a big way to stay ahead of our competition. Next slide, please. Uh, this slide is basically just a snapshot of a few turnkey projects done at HCL in the very recent past. So since we work with our technology customers and we work on their next grade projects, so we also have to follow a lot of restrictions in what information we can divulge. So while I say these are the recent case studies, these are not the latest ones which are in the latest technology nodes, but these are a little older. I would say close to 2 years old projects. But nevertheless, it basically highlights the fact that we have worked on complete end-to-end product chip realization for our customers in various industry domains. So, for example, consumer electronics, uh, automotive, uh, uh, power management, uh, consumer electronics. So chips from the most of the industrial domains you'll find done at end-to-end fashion at HCL here. Next slide, please. So next is the career options that are available at HCL. So we can move to next slide, Min. So depending upon whether you are fresh from college and you take a decision to pursue a VLSI career, or whether you have been a professional or and already a practitioner, there are options available at HCL. So you can join at the entry level, at the engineering level, and get trained at HCL and pursue your career, which can go all the way up to heading the a function for a given uh, domain, or you could start at enter at various other career options that are available here, uh, and grow and mature from there on. So we have career options at all levels available, and since we have a 25 plus years of genealogy here, so we also have a perfect time tested and perfected career ladder and evaluation process, and therefore a growth roadmap for our engineers. So it is quite common that people join and then they uh, continue for their entire professional career at SCL. So that's what we offer, and we look forward to hear from many of you and become part of our journey here at SCL Vietnam. Uh, so uh, so I think so. So please do reach out to us. I'm sure you will have a very satisfying and mutually beneficial career at HCL. So this brings to end of my short talk on what VLSI industry is about and how HCL is poised to address this, and where do we stand and what option we provide to you. So this brings to end of my our discussion. So if there are any questions, we can probably handle them. So I'm done with my presentation.
So thank you for the enlightened sessions. So we get a lot of knowledgeable, and I'm sure some of us are contemplating starting our career in VLSI. Yes. So thank you everyone. We appreciate you still being here. And one more time, thank you, OP, for your wonderful presentations. So hope that today event will bring you useful knowledge. If you have interested in career opportunity at HCL, please visit hclvietnam.com and find out available jobs. Thank you to all attending our virtual session. See you later. See you, OP.